Welcome. Let me say something about Morse-Sard. It's something I've worked on in 2015. If we have a graph which is a manifold and we look at the level surface, we should get the manifold of dimension 1 less. And the framework is graph theory. We work with a notion of manifold which has occurred quite a few times already. It's a very natural definition, inductive definition, nice to work with. So a manifold, a d-manifold, is a graph such that every unit sphere is a d-1 dimensional sphere. So for example, for an icosahedron which we have here, every unit sphere is a circular graph with 5 elements. That's a 2-manifold. It's also a 2-sphere, because if you take one point away, it becomes contractible. So this is the definition. It gets started with a 0, which is the empty graph is the -1 dimensional sphere, and the 1-point graph is contractible. It is the 1 element, the 0 element in the ring, which we have looked at, and we have arithmetic of graphs. One of the notions which comes is the dual of the disjoint union, which is the join, the Zykov join operation, which preserves spheres. So that will be playing an important role. Is again the definition of what is f equal to 0. If you have a coloring, so here in this case I have a 2-sphere. I just put some random function there and generated then the graph f is equal to 0, which is a natural 1 sphere in this case. So when I worked on this, I was looking also at what happens when you take 2 functions. So if you have a level surface and on that surface another function, then you have a hypersurface. In that hypersurface is a Codimension 2 manifold. What happens is every time we look at this f is equal to 0, we go to the barycentric refinement. So if you have 2 functions, you want to look at the level surface or variety, kind of where f is equal to 0, g is equal to 0, then you have to work in the second barycentric refinement. Even worse, if you look at the g is equal to 0 on f is equal to 0, that's a different graph than f is equal to 0 on g equal to 0. So somehow I was excited, you know, this is quantum mathematics, right? This is finite mathematics, space geometry, where everything is finite and quantized. So, oh, maybe there's a natural kind of order, right? So we have non-commutativity also here. This should be essentially part of commutative algebra. So if f is equal to 0 and g is equal to 0, this should actually be, you know, independent of the order in which you are looking at things. And last week I started to really understand what is going on. This is a continuation. When f is equal to 0 and g is equal to 0, we can define that directly in the barycentric refinement. So we have 2 functions f and g on a manifold, and now we look at all the points, all the simplices where both functions change sign, and also where these 2 functions should define at least 2 different or 3 different values. So that's the definition. So a few lines of mathematical code can produce you nice surfaces. Maybe I'll show you here a surface which is a 2-dimensional surface in 4-dimensional space, just obtained by 2 random functions on a relatively small 4-dimensional sphere. It's already quite impressively complex. Or here's another example where we have a genus 2 surface which has 2 holes, and we have also just randomly chosen 2 functions on that relatively small graph. Or a third example where we have 2 tori, and then we rotate around to see how these level surfaces are level surfaces in the barycentric refinement. And there is a theorem, analog theorem to the theorem I proved in 2015, is that this is always a manifold or empty. I mean, if you are out of the range, of course, then in this case, for example, if you look at the level surface where f is equal to 100, of course that is empty. That's like in calculus, when we are looking at level surfaces of functions, we have generically hypersurfaces, and that Sard theorem, the Morse-Sard theorem, tells you from 1938 to 1941 tells you that you always get manifolds with probability 1 in the target space for almost all values in the range is a manifold. You just have not to take the function values on the word is. And it generalizes, of course, to arbitrary dimensions. You have m functions in a d-manifold, and then you have a d minus m dimensional manifold. So you can use this, it's very practical, you can use this to generate, you know, manifolds with relatively small graphs. So random surfaces, random manifolds. By choosing the functions randomly, you generate random objects, and you could study that. Possible range of Euler characteristic can occur, what is the statistics, etc. There are many interesting questions one could look at. So the absolute key is to understand that the barycentric refinement has a very nice hyperbolic structure when you have a manifold. So hyperbolic structure means there is a stable direction and unstable direction, and every simplex, of course, has kind of the stable part are all the simplices which are contained in it, and the unstable part are all the simplices which contain the simplex. Of course, the simplex itself is not in the unit sphere, but the unit sphere is then naturally the join of the stable and unstable manifold, stable and unstable part, like in dynamics, right? When you have a stable manifold and an unstable manifold, and you intersect it with the unit sphere, then the sphere is the join of the stable and unstable parts. If you have a manifold, you intersect it with a sphere, you get the sphere. So for small spheres, so in this case, that's really coming from hyperbolic dynamics, something I've grown up in, and it's very nice to see this hyperbolic structure here. The dimension function is a natural Morse function here, and these are really stable and unstable manifolds in this Morse complex. And every point, every simplex is a critical point, and the dimension determines whether the index is +1 or -1. I add up all the Poincaré-Hopf indices, you get, of course, the Euler characteristic, but that's the definition of the Euler characteristic. So it's a very natural, also Morse framework. And so this is actually then the closure of a point. This is the smallest open set containing, so that's the star. Okay, now what we have is we have to show that we have a level surface, or a level hypersurface, that the unit sphere in that set is a sphere, and it should be a sphere. So the unit spheres of the d-manifold are d-1 dimensional, so if you have two functions, we should have a d-3 sphere. It's just according to the definition, the S plus doesn't change, because this, we look at all the elements where things change sign, right? If you are changing sign, and also if you change sign on an edge, then every triangle which contains this edge also, the function changes sign, so this is contained in that. So the S plus doesn't change. The S minus now just gets reduced. You can also use somehow the induction. This is the boundary sphere here is a k-1 dimensional sphere, and then we are looking at the codimension 2 surface in that sphere, and because it's so small there can only be spheres. So but we can also understand it directly, just this S minus H is now just a sphere again of dimension 2 smaller, and then the hyperbolic, with a hyperbolic construction, you have the unit sphere of H is the join, like before, it's the join of the stable and unstable sphere, and so the stable sphere has reduced dimension 2, the unstable sphere is the same, so the sphere of the whole thing is a sphere of dimension, codimension 2 of the original sphere. So that's the that's the proof. And the best way to convince that this is really working is to just show pictures of these beautiful manifolds you can get by taking a relatively small graph, take two random functions, and just see what you get when you look at the level surface. And the examples which I kind of chose first are kind of naturally four manifolds. So maybe I'll stop here and we'll continue next.